So for those of you who don't know me, I'm Paolo Valente, and I'm from the University of Modena and Reggio Emilia, and I'm an external contractor of Linaro. So the first thing I wanted to tell you is that fortunately results are much better than those reported in the abstract for this presentation, because I was still working on this when I wrote the abstract, and then results became even better. I will start by telling you what BFQ already achieved before these new changes. Then I will use this to introduce the need for these changes, because these changes are based on improving some mechanisms that are the same that provide the previous achievements. And so I will show you these enhancements. Basically, it's an improvement of the throughput reached by BFQ by about 150%, and an improvement of the responsiveness by about 80%. Basically, it means that in my test, applications start 80% quicker than before after these improvements. And finally, BFQ is now a little bit faster, a little bit quicker to execute. The same results are available, are reported in this new LWN article. Here is the link, but it's only for subscribers for, I think, another week, more or less. Then it will become free for everybody. One last thing before I start. Mike and Elsie told me that there should be some guys from the data center group. Anybody from the data center group here? Okay, so maybe, I don't know, they won't come, or maybe they will come later. Okay, so these are the previous achievements. BFQ proved to be very effective in reaching a high throughput, more or less 5 times more throughput than the, how can I say, classical solutions to control I/O. So this is for server-like workloads. And at the same time, BFQ provides much stronger guarantees on I/O bandwidth. So more control and higher throughput. This is reported in this post on Linaro's blog. This post in its turn refers to another LWN article providing the technical details for this result of BFQ. On the other side, for a personal system, I made this new demo on a Chromebook that shows the performance of BFQ in terms of responsiveness, and I have the demo here. Okay. So this demo is on this Chromebook that Google sent me. And basically I start an emulated download, a download on a fast network. I just emulate it with a dd command. And while this emulated download is in progress, I simply try to start Chrome. The first time I do this with MQDeadline, which is the default I/O scheduler in Linux. Then I will do the same using BFQ. We're just replacing BFQ, but just using BFQ instead of MQDeadline. So in a moment in the demo, let's see. Okay, yeah, that's the setting of the scheduler. Then I start the workload. I wait a little bit for the write back to actually start, because it starts only after enough pages are dirtied. And now probably I've already clicked, but you don't see anything, because what happens is very simple. Chrome doesn't start. It will start only after the download is finished. So I hope it is not too much, probably another 10 or 20 seconds, so I will think of something to say. Oh, wow. If we, No, don't do that. My connection seems to be gone. Okay. So even more waiting. Let's see whether, okay. No. Maybe if I, okay. It's no SSD. It has an MMC. Oh. Yes, yes. It's a. Let me. These are more or less the details on the machine, and I didn't find the exact name of the MMC inside this machine. So that's why I put all the details of the machine so that you know. Yeah, it's a slow one on purpose. Okay, so the cause of the delay was not my network. Believe me, it's Chrome not starting here. So let me. Okay, maybe more or less here. So after waiting for a lot of time, Chrome should finally start. It's almost. Okay, finally it starts when the download finishes, but then the system is still not so responsive. So I had to wait a little bit to to send Chrome away. And when I finally made it, I did the same using BFQ. So again, after the switch to BFQ, okay, the starting of the download and the waiting a little bit for the writes to start, and then finally, when I click there, Chrome immediately starts, and it's perfectly responsive. You didn't flash the page cache? Yes, absolutely, yeah. Yes, yes. Otherwise, it was a simple trick. But, I mean, with all these writes, actually... Anyway. Okay, so then other good things happened, like there was a new test, a new phoronics test in which BFQ proved to be the best scheduler overall over all the tests with our disks. The same didn't happen with SSDs, but that was due to other issues that I want to talk about. I hope that in the next phoronics test, maybe BFQ could get the same result as for our disks. A new operating system switched to BFQ. Android should switch to BFQ when they switch to a higher kernel version. OpenSUSE and SUSE are evaluating a switch to BFQ. The same for Fedora, and other systems are considering this switch. Okay, now, as for these improvements, they are related to the main goals of an I/O scheduler, which are boosting the throughput while controlling the I/O and doing all of this very quickly. As you can imagine, it's not easy to do all of this at the same time with every workload. In particular, there are some workloads that trick BFQ heuristics, and so the throughput goes down exactly because of the same mechanisms that help BFQ reach a high throughput with other workloads. So the first class of improvements that I'll show you tries to fix this problem. On the opposite end, tuning the scheduler for throughput may, what can I say, may make responsiveness worse. And the other improvement tries to address this other issue. And finally, BFQ is heavier than the other I/O schedulers, so I try to make it a little bit faster. Okay, let's start with this throughput improvement. And to introduce it, here is a scheme of how BFQ works. Basically, we have processes doing read and write operations. I/O layers translate these operations into block I/O requests, read and write. These requests go into the internal BFQ queues. Basically, there is one queue for each process. It's a little bit more complex than this, but for this presentation, it's enough to say so. And then BFQ services each of these queues one at a time for a while. A problem with this service scheme is that if you serve only one request at a time, if you send to the drive only one request at a time, then you get a low throughput. And this figure shows the reason behind this simple problem. We'll start with these obvious things to get to the a little bit less obvious part of this improvement. So suppose that you fix the I/O depth to 1. So you only want to have at most one pending I/O request, which means that you start to prepare a new I/O request only after the current request has been completed. You might also prepare the new request in advance. What matters is that you dispatch the new request only after the current one has been completed. In this case, this is what happens. In this figure, we have these down arrows that represent dispatch events. So after a dispatch, you have the service that starts in the drive. This is the service of the request. So the projection on the x-axis of this rectangle here is the start time of the service, while the projection on the right-hand side is the finish time of the request. So TS is the service time of the request. When the request finishes, you start to prepare the new request and you send it, but it takes time to process the new request. I've called it TP, processing time. Because of this processing time, you have your drive doing a sort of duty cycle with one request, 0, 1, 0, 1, 0, and of course this lowers throughput. So the simple idea is just prepare a new request before the previous one has been completed. And this is an example with an I/O depth equal to 2. So R1 is in service, but we immediately dispatch also another request, R2. When R1 is completed, since R2 is already inside the drive, it's in the queue of the drive, R2 immediately starts to be served. By doing so, the processing time to prepare R3 is absorbed by the service of R2, because I start to prepare R3 only when R1 is completed, because I have an I/O depth 1 here, so I want to go back to 2. So when R2 is finished, R3 is already here, and the drive is always working, full speed, maximum throughput. This is a simple example, but we can do the same example with higher queue depths and higher I/O depth. The problem with doing this is that we lose control, which is shown in this figure. Suppose that we have two queues. Q1 must receive twice the bandwidth of Q2. So for every request of Q2 served, there should be 2 requests of Q1 served. But Q1 does synchronous I/O, which is absolutely typical with reads. Reads are typically synchronous. The process does one read, then blocks, waiting for the completion of the read before issuing the new one. While Q2 does asynchronous I/O, which is typical with write back. So Q2 receives a new request whenever it wants. In this case, what happens is something like this. Suppose that the beginning is very lucky, so Q1 is already in service. A new request from Q2 is queued in the drive. I've put here an exclamation mark to say that we wanted another request from Q1 here, not Q2, because we wanted to serve 2 requests from Q1. But this is impossible, because Q1 is blocked, waiting for the completion of its current request. So only a request from Q2 may arrive. Okay, and this goes into the queue. When this request is finished, again, only a request from Q2 may arrive because there is the time to prepare the new request from Q1. So finally here, a new request from Q1 arrives. But there is another problem. At this point, we are inside the drive, and the drive is free to choose whichever request it likes. So the drive might do this, and it does do this. It might go on serving requests from Q2, for example, because the requests from Q2 are sequential, and this maximizes throughput. As you can see here, Q1 is definitely not receiving twice the bandwidth as Q2. We have lost control. So, to address this issue, BFQ serves one queue at a time, one BFQ queue at a time, one internal queue at a time. Which means that if you have a sync queue that becomes empty, BFQ just waits. BFQ plugs the I/O coming from the other queues and waits until finally a new request arrives from the queue in service. There is, of course, a timeout because we cannot wait forever. If that queue will never have a new request, then we would be stuck. So there is a timeout in this waiting. And this causes a problem. Typically, only one core sends requests into a BFQ queue. And one core is slow. It is usually slower than the drive, the core is slower in inserting new requests than how the drive is fast in draining the same queue, in consuming requests. Simple example with this hardware here, the device takes about 14 microseconds to serve one request, while a single core takes 200 microseconds to prepare and dispatch a new request. So this thing happens. Starting like in the previous figure, R1 is already here, R2 is queued, so when R1 finishes, R2 is ready. But after R1 is finished, we start to prepare the new request, but TP is too long. So the service of R2 cannot absorb the time needed to prepare a new request, and there is a service hole. Again, the drive is idle. And the problem, of course, goes on if TP is even higher, then the holes are larger. All the things shown in these figures are not, how can I say, just theory. This is exactly what happens inside drives. So the idea in BFQ is just this. Inject requests from other queues in these service holes. Just it. Just drop other requests in the holes to keep the drive busy. The hard part in this is finding the right amount of I/O to inject, because we want to boost the throughput, but we don't want to break service guarantees. That's the hard part. How much do we inject? And to guess the right amount of injection, BFQ, before these changes, BFQ did this way. It measured the bandwidth of every queue before the queue underwent injection. Then, again, it measured the bandwidth of the same queues after the queues underwent injection. If, after the injection, the queue had more or less the same bandwidth, enjoyed more or less the same bandwidth, then at the next occasion, BFQ increased the injection. And then again, it compared the new bandwidth with the previous bandwidth. If the new bandwidth was still high enough, then at the next round, more injection, until the new bandwidth of the queue becomes too low, and in that case, it decreases injection, and so on. Okay, this is more or less the idea, finding the right amount of injection by attempts. There is a problem with this approach. To have a reliable measure of bandwidth, we need a queue to be in service for long enough. And this is not always the case. With many more workloads, this doesn't happen. So bandwidth measurements are not reliable, and the solution becomes imprecise. And for this reason, it was used only for random I/O, because random I/O has large holes and the service time of each request is small. So you have less risk to do damages. The new version, these changes introduce a new way for adjusting the amount of injection, and simply, instead of using bandwidth, instead of measuring bandwidth, now BFQ measure service time of single I/O requests. And this is always meaningful. Even if a queue is served for just one request, still that time is meaningful. So by comparing the service time with and without injection, BFQ decides whether to increase or decrease injection. Relying on this new mechanism and on the precision of this new version, now injection is extended to every kind of I/O, and this is the result with a dbench test, which is one of the workloads for which BFQ performed worse. This is the previous performance of BFQ. This was the throughput before this change, and this is the throughput after this change. The throughput becomes equal to that reached by the other I/O schedulers, and this value is the maximum throughput that you can reach with this workload, because this workload is basically random I/O. So to reach the maximum possible throughput, we have just to never plug I/O, just send every request as soon as it arrives. And this is what the other I/O schedulers do. So now BFQ is on par, but there is a difference. This is BFQ, same throughput, full I/O control. Other I/O scheduler, same throughput, no I/O control. And you will see this in the next figure. Next improvement, responsiveness. That plugging that I showed you lowers throughput. For this reason, BFQ tries to plug I/O for as little time as possible. 8 milliseconds was the previous value. A problem may occur. Some BFQ queues may have new I/O too late. And in this case, they lose their bandwidth guarantees because of that loss of control that I showed you. So if the queue doesn't make it to issue to have a new request in time, BFQ will switch to another queue, and that queue will lose its chance to have its bandwidth guaranteed. This is a problem with queues that carry the I/O of applications that are very time sensitive. For example, when you are starting a new application, you want it to start as soon as possible. So in that case, you don't want the bandwidth guarantees of that application to be violated. Simple solution has been to just increase the timeout for those specific queues, and this very simple change provided these relevant results here. This is the startup time of GNOME terminal in two cases. While 10 files are being read sequentially in parallel, and while 5 files are being read sequentially in parallel, plus 5 more files written sequentially in parallel. I hope this is clear. We had a discussion with Matthew about how to better say this. I'm not sure I said it the best way. Anyway, with this load, the startup time of GNOME terminal lower is better here. Went down from 1.2 to 0.8, and in this other case from 2 to 1.2. As a reference, this is the startup time with the second best I/O scheduler after BFQ. As you can see, there is a certain difference. This is the consequence of what I told you. No control with these other schedulers. Finally, reducing execution time, I will spare you all the description here. Simply, there is a mechanism called queue merging, and this is useless with SSDs for several reasons. This additional mechanism costs time, CPU time. It costs time. It is useless. Time is critical. Execution time is critical with SSDs, so simply I disabled it with SSDs. This is the result. The execution time of BFQ decreased a little bit. This is the total execution time. It is the sum of the execution times for each scheduler event. Insertion, extraction, that is dispatched to the drive, and handling of the completion of a request. So the amortized cost for each event is about 0.6 microseconds. As a reference, here is the execution time of the fastest I/O scheduler in Linux, MQ deadline. This means that BFQ takes 0.4 more microseconds to execute for each event. This seems to be a good result if you consider that MQ deadline is just 800 lines of code, while BFQ is a little bit more. Still, it only about 3 times as fast.
Which CPU?
I didn't write it, sorry. It's the same as...
Which CPU?
Yeah, for... where is it? This one. Yeah,
pretty standard.
It's a mobile CPU. It was a high-end mobile CPU. Was. Yeah. Now it's average speed CPU. And I think this is more. Yes. So now, where in which case you cannot use BFQ because it is too heavy, but you can use MQ deadline. The cases where this happens now, the set of configurations for which this happens has reduced to which configurations? The ones in which you can afford handling I/O in the kernel, which means that you can afford a context switch between user space and kernel space for every event, for every I/O event. And you can also afford these extra microseconds for MQ deadline, but you cannot afford this extra 0.4 microseconds. So the set of configurations should be rather small, as you can imagine. You can afford all the rest, but you cannot afford this 0.4 extra microseconds. Okay, and I think this is all. Okay, that's all. Any question?
I can start. Like when I see the first slides, like what you are battling here, you're battling the firmware of the hard drive, essentially. They are this one with the queues. Let's go on. The previous. This thing where the drive keeps dispatching from Q2. It just goes on. Yeah, this one. This phenomenon.
The loss of control. Yeah.
The loss of control.
Yeah.
That feels like this loss of control comes from the firmware of the hard drive. Or where does it come from?
There are 2 parts. Up to here, it's our fault. In this part here, it's the drive's fault. And this depends on the firmware of the drive. Some drives do this. They go on serving the same queue, even the drive doesn't know that it is a queue, but it goes on serving the same kind of I/O, for example, because it is sequential. New drives tend not to do this any longer because this worsens latency. So you are in the hands of the drive for this part. Yeah. This part is your fault. Yeah. Even without this part, you still don't get 2 times Q1 and then Q2. 2 times Q1, then you still don't get it, even here. But because of this additional problem, you might also have a sort of starvation for Q1.
And that might be due to the drive being designed for throughput and not
Yes.
control. Okay, I
Exactly.
guess.
And not for latency.
Yeah, so they have all these benchmarks and competitions for throughput, and that has been maybe a little bit too much in focus for the drive manufacturers, and this is why they have constructed drives that start to act like that.
Yes. Now they are moving to, I mean, new drives, but all this information are not so publicly available. This is what I'm, they are trying to avoid this because they realize that this is a problem. But you still have this one. Yeah. Yep.
Do you think we still see that problem on the going down to slower devices when the really fast SSDs have fixed this, but the UFS and eMMC might still take years to get to see the same fix? Or do you think that new devices across the board would have changed behavior as soon as they detect there is a problem?
It's very hard to. I don't know. I don't know. But still, I think that how can I say? Whatever they do, it doesn't solve this part.
Yes.
So, yeah, but I don't know whether the even slower devices will be geared towards low latency very soon. I really don't know.
So I can only say what we've seen in other
probably you know better
optimizations.
than I do.
So what I have observed in the strategies around garbage collection inside of flash devices, we do see the improvements first being applied to the high end, where we have an SSD for the enterprise market.
Yes.
Then it takes years to make that same improvement to the desktop market, and then further years to get it into mobile devices. And then on the tail end, there might be SD cards which don't have any of the optimizations even now.
Yeah.
And my guess would be that something like this could happen across the same markets where it just takes years. Also, because the controllers on the low end are very simple. They only have kilobytes of memory instead of gigabytes of memory.
Yeah. Yeah. Yes, I guess so. But I don't know much more than you on this.
Yes.
Yeah.
So I've tried talking to vendors about other problems, and it's very hard to get any information out because that's
Absolutely.
always they're competing on those trade secrets.
The most transparent answer I got so far is use our simulator, which is SSD Explorer. Maybe you have heard about that. So there is this simulator, and somehow a certain group of vendors, I don't know exactly, but they use this sort of common ground so that none of them has to reveal anything, but they have this simulator where probably you can configure any of those features, even if they are not signed, like this is in this drive, this is in this other drive. Yeah. That's the best answer I got, and they told me, okay, just try all the possible combination with this simulator and you will know everything.
Yes. The other answer that I got from one vendor in particular is that they sell market-specific drive firmware. So in a Windows laptop, you would see a different firmware on the same hardware eMMC compared to a Chromebook, and yet another firmware for an Android device, because they're selling to different things and they try to tune for given operating systems. And then if you get in the industrial market, you might see something completely different where they put additional hardware in to make it more reliable.
I was going to ask about the nature of the algorithms inside BFQ now that you worked a few years with it. What is the like the type of arithmetic and so on going on there? Are you like what do you use? So, for example, like what would be your dream features from the CPU to execute it quick? Can it be implemented in hardware accelerators in the future? That's like an open question.
Yeah,
spaced out. Maybe.
I could answer this way: the future is parallel. So, instead of waiting for CPU features that could help BFQ, but I don't see any particularly heavy operation in BFQ. The most complex thing is a low-pass filter done through a moving window, so it's not that, I mean, that heavy. The main problem of BFQ is that it is not parallel. So this time here is a whole suffered with only one core executing. I don't remember whether I put this somewhere, single lock. Okay, no, I didn't. Oh, it's here. Single lock protected. That's the problem. That's the problem. All other cores are stuck. Why? If they try, of course, to execute BFQ, they are all stuck. Only one core executes this. So this is the next thing. I'm working on that.
Is it a sleeping lock or a spin lock?
Spin lock.
Okay. So they're actually not doing anything else either.
Exactly. Yes. And so this is the next thing. I am trying to make some parts of BFQ parallel. I mean, conceptually they are already parallel. The problem is that they are protected by the same lock. So the next small step will be to try to introduce new locks, and basically the idea is this one. We have several queues, so my idea is to try to put a lock on for each queue. So not a single global lock on the scheduler, but a lock for each queue, plus that same single lock protecting only this part here, because this is the common part. There are many things that are done only for each queue, independently of the other queues. So that's the new challenge, let's say so. Yeah, we'll see. Because the execution time of BFQ, of course, it's higher than that of a scheduler that does almost nothing. But it's not that, this is not like 10 times or 100 times higher. So if you can do this in parallel, every piece may even become more or less as long as this one, because also this one is with a single lock. So yeah. Other questions?
Given that you're talking about the locking, is there a chance that you can make the part where you expect a single lock to go beyond that by making it lockless using RCU or some other lockless manipulation of the structures?
Yeah, this would be the next dream. Okay. Yeah, absolutely, yes. I'd like to make the enqueuing and dequeuing, these queues here, lockless. Maybe even without using RCU. Because there are some lockless solutions.
RCU might not be the best solution, but if you want, we can go through that one day and see what would have to be done. Because lockless insertion and removal from a queue is not a new problem.
Exactly, yeah. Exactly, yes. Just to use what, I mean, it's already available, just to exploit it in BFQ. And I'm just recalling now that this multi-lock scheme is the same as Kyber, which is more or less what you told me some previous Connect, when you told me, could you integrate Kyber and BFQ? I had a look at Kyber, and the main idea that I had from Kyber was exactly that. Kyber is more or less, I mean, not that, it's not as heavy as BFQ, but not much less, but it's completely parallel. Everything is done in parallel. That's the strength of Kyber. Yeah. Okay, could you please? No data center guy, right? No one. Strange.
So how does this play together with all the multi-queue per CPU efforts that are happening? So as far as I understand from blog people I know, there's been a lot of work to try to make sure that block queues are fully aligned to per CPUs, that they're always only local. You leverage your local caches, you leverage like the interrupt always comes on the CPU where your data is, etc., etc. How does BFQ play along? Because that I mean, everything you explained so far assumes that you have this global thing that knows the whole world, and the whole idea of block and queue is that you don't.
Exactly.
Which means you get all the way back to all the starvation problems if you keep them separate. So how does BFQ solve that?
We are mixing two things here. Executing stuff in parallel, and so not doing so means going slower. And this is one problem with BFQ. It is what I talked about. The other problem is, if I unleash this parallelism, then I risk to lose control. My idea to unleash this parallelism, if I make it, is to do this way. So not just do everything in parallel in the wild, but try to do it in a controlled way.
But still with each queue on its own local CPUs that still gets dispatched on something that's there, it's just that the entity would be different throughout, roaming throughout the system. So the dispatcher would be different based on the time scheduling slot you have for, I don't know, for the...
Which part you mean to be independent?
You have two CPUs, right?
Yeah.
Each CPU has a queue associated with it.
Yeah, a software queue.
No, a hardware queue.
No, the hardware queues depends on the drive.
Yeah.
There are two
assume you have a hardware queue per CPU. I mean, that's the normal case, unless you got an EMC, which I'm not going to even bother with.
Yeah.
So
well, actually, it's this. Oh, okay. Let's say so.
Anything NVMe, which is the interesting case, is going to have basically as many queues as you have CPUs.
Yeah.
Unless you have really cheap parts. But
yeah.
In the normal world, you will have as many queues as you have CPUs, which means if you have two CPUs, you will have one hardware queue per CPU.
Yes.
And the starvation problem you were explaining applies there exactly the same way, right? Because hardware firmware may just only serve the second one because that happens to be sequential, and then, well, tough luck. So you said you would like to solve this the same way, but this still assumes you have a global view. So would you basically, in software, keep the second hardware dispatcher from servicing anything while you're trying to make sure the first one works?
No.
Or
in your example, I think that may happen is that you have one hardware queue serving this stuff, and the other hardware queue serving the things that are injected.
Which means you no longer get CPU locality.
CPU, sorry?
CPU, you no longer get the locality that you would get with multi-queue.
No, yeah, you do.
Oh, you just move the application to the data.
I don't know whether you can say it that way, but I mean, you still have, how can I say, every hardware queue receiving its own requests. BFQ is just a sort of, how can I say, semaphore, saying stop. If BFQ doesn't say stop, those requests just flow to the queue, using that same block and queue architecture, locality, and all the rest. BFQ just sits in the middle and says to someone, stop now. The fewer times BFQ says stop, the faster you go. But all the rest is the same. BFQ doesn't change anything about locality and all the rest.
Okay, I see. So the hardware queues would still get dispatched to by the individual CPUs. You just have this global entity that basically says, well, wait here now.
Exactly, because all of this is outside BFQ.
So part of the problem, as I see it, is the amount of parallelism, where we have multiple processes, each on their own CPU, being served all the way down through the kernel to the hardware to individual threads on an SSD, but then trying to access the same memory cells.
Yeah.
So we have something very, very parallel all the way down to the point where it cannot be parallel.
Yeah.
And then we get the effects of loss of control, because those two processes on one end we try to maintain fairness, when the other end has no idea about the
Exactly.
fairness. And there has to be something higher up in the stack that guarantees the fairness before things go down.
Yeah.
Right, right. Okay.
Yeah.
I think I'll need a couple of hours to wrap my head around this, but
Yeah, I mean, it's tricky stuff. This is tricky stuff.
There's always more problems than you think there are.
yes, that's
If
exactly
if
right.
you want, the intuition is since what Arne says happens, you try to control the amount of interference that may come from the other queue. You have a sort of main queue and you want to make that queue happy. But then you still want to reach a high throughput, so you want to try to saturate the throughput by sending only the extra requests that you can send, so as to reach exactly, more or less, that maximum throughput. Because the problem is when you go in above that level, then the contention begins inside the drive, and someone has problems because of this contention. If you are so smart to send just what can be sent in the idle times for the drive components, then you win.
I
It's
agree,
not
but, like,
easy. I mean,
the thing I'm having a hard time to wrap my head around is that I assume an NVMe has its ideal spot at 16 parallel operations. Right?
okay.
So you basically, with your logic, you would need to find out that you want to always have 16 running in parallel. You don't want to have 15, you don't want to have 17. You always want to have 16 running processes in parallel, because there just happens to be the hardware layout, or maybe that NVMe is actually backed by an NVMe storage that just happens to be spreading everything across 16 servers for
Yes.
your, right? I mean, you don't know, right,
You don't know.
what the hardware topology is behind this, but we're getting another dimension of the problem. I mean, everything you explained is essentially one-dimensional, right? You're always assuming that you, or at least in the slides, I'm pretty sure you
Yes.
don't, but
Yeah.
the slides always show everything as one-dimensional. You basically eventually go down to a single queue that can be processed, but real-world drives work in parallel, because there is no single cell eventually.
Yes.
There's I don't know, like 64 different chips that maybe they can drive in parallel, right? And depending on your I/O pattern, you may drive them in parallel, or maybe they all get contended on a single chip because you just happen to access address ranges that overlap.
Yes. Yes.
But
But yeah.
that's something you
That-
need to
that's
find
because
out by software
Yeah.
empirically
The-
during runtime.
The parallelism you are thinking about is introduced by this injection. Of course, I draw it like something sequential, but
Yeah.
it is not.
Okay.
It is not, because while these requests are in service, they are being served inside the drive, but the CPU is idle. And the cores are idle, and they're pushing new I/O requests and treating the drive as a black box. The how can I say? The consequences of what you say, like 16 parallel units inside the drive, you see them by measuring the bandwidth that you get, as if it was a black box. Until nobody suffers, you go on pushing more requests, which
Okay, I
means
see.
that you are increasing the parallelism.
Okay. Okay.
And this is very much this part of the problem is very much the same as the buffer bloat issue that we see on networking,
Yes.
Yes.
where we have multiple streams sending as much data as possible, and then you have the single shared medium that they need to get on. And if you have buffering somewhere, which you usually have, then you need to manage those buffers, because otherwise you might starve
Yes.
one of the
Yes.
high up in the stack users.
Yes. Yes.
Exactly.
Okay. I think I'm slowly starting to grasp
Exactly.
it.
Yeah.
Nice. Thank you.
Thank you. Okay. Thank you.